All right, so let's get started. Welcome to the second day of the Professor Knuth Days at Brown. I'm going to say just a few words to introduce Professor Knuth, although Eli Upfall introduced him yesterday, and of course there is no need of an introduction, but I'm just going to say a few things. Aesthetics is very important in inspiring, and a few weeks back, when Professor Knuth accepted our invitation, I was very happy that day, like all of us, but I was double happy because Bob Dylan was awarded the Nobel Prize for Poetry in the same day. So I am in class lecturing on the Knuth-Morris-Pratt algorithm. So I wrote to Professor Knuth a message of enthusiasm for his acceptance of the lecture, and I said, you know, the Turing Award nomination for Professor Dijkstra said that due to him we appreciate programs like we appreciate good literature. And I said in my email to Professor Knuth that what Dylan taught me is that algorithms that are optimal from the point of view of the analysis of algorithms and are elegant and practical are like poetry. So I think Professor Knuth writes poetry in his algorithms. So I thought I would say what I think are Professor Donald Knuth's axiom, principles, at least the one that I learned from his books. And I'm going just to venture a few of them. Axiom 1, work on the hardest problems. Axiom 2, be a mathematician of the discrete and continuous mathematics. Axiom 3, be an intramath, intersciences, and cross-cultures scientist. Axiom 4, know a lot, really a lot of mathematics and its history. Axiom 5, aesthetics is very important and inspiring. And axiom 6, work at the same time on the most theoretical and most practical aspects of a problem. But these axioms are also John von Neumann's axioms. Both of them are really superhumans. Just look at the output of their scientific creativity. Here is John von Neumann's complete opera and books, and here are only the 16 books that I have from Professor Knuth. There are 30 altogether, so imagine the pile is that much. So in my view, it's a very similar creativity output. So I would say here is a superhero, you know, with superhuman powers, the two of them. So this morning, I had the pleasure to accompany Professor Knuth at the Cathedral of Saints Peter and Paul, where Professor Knuth played the organ there, the majestic organ there. And he played his composition Fantasia Apocalyptica, where he showed me a theme inspired by Superman. Well, I know two real-life superheroes, von Neumann and Knuth. And one more thing, axiom 7. And in the end, the love you take is equal to the love you make. All right. I introduce now Professor Knuth for his lecture.
Well, okay. I guess I am embarrassed. But anyway, thank you for the very generous introduction. And although I am a little disappointed that you only said that my poetry was in algorithm, because I presented some poems yesterday. Okay. No, but it's a terrific honor for me to join all the illustrious people who have previously given the von Neumann lecture here at Brown, as well as yesterday, where there was a fantastic list of people giving Kanellakis lectures. So my head is, you can see it's swelled up a bit here today. So what I want to talk about is something, again, it's always a pleasure to give a lecture about something where you have a good story to tell, and I think I got something that a few of you will like today. But in a way, I'm also here to sell a book. It makes a wonderful Christmas present, and it's I don't know what they're charging for it now, but you can also get it in ebook form if you like that, but or both, so it's the middle third of volume 4B of the Art of Computer Program. I haven't written the first third or the last third yet, but this is the middle third, which is which turned out to be I'll talk more about it. But I put it on the scanner, and behind is volume 4A. That you can barely see it. I just wanted to see what would happen, if I scanned it. So you can see a little bit volume 4A of the Art of Computer Programming. And so volume 4B is probably going to have a lot of this stuff, of course, with bugs removed, hopefully as I get going. Now the next page, small type. I don't expect you to read it, but this is the contents, and the main thing I want to point out is that there's 300 pages in this book, and it's all about satisfiability. Now, why did I wind up devoting 300 pages to this? And I guess the main message I want to get across today is that satisfiability is something that turned out to be extremely important the more I looked at it. And so it's not only something that should be of interest to people on one of the floors or one of the corridors of one of the floors of this building, but actually people on every floor might very well find that satisfiability is going to be their friend if they know more about it. So this was kind of a surprise to me, because I never heard about it when I was an undergraduate student, but I heard about something very closely related. But still, it wasn't. I never thought it would be worth 300 pages in a book. And well, I set the table of contents of the Art of Computer Programming sort of in 1962, and so I didn't anticipate that I was going to have 300 pages about satisfiability at that time. And so what it turns out is this 300 pages is all section 7.2.2.2 of the Art of Computer Programming. I had to graft it into the table of contents, because it turned out to be something that became important. About the year 2000. In 1999, I wouldn't have done much with it. But as you'll see, it became unexpectedly interesting. And the other thing is, why would it's kind of, well, it's certainly going to be the longest section of the Art of Computer Programming, and it's not really ideal to have a section that's 300 pages long. It'd be nicer if I could have broken it up into 5 subsections, or 10 subsections or something. 10 subsections at 30 pages each. Right? 30 pages is a nice thing. However, this is already section 7.2.2.2. There's no room in the table of contents for another column in there. And the format of my books doesn't allow for extra decimal point in there. So I was stuck. And but I think if you read the thing, you'll see that there's sort of a segue from one topic to another. You don't have to really break it down. But it might have been better if I could break it down. But I never saw a good way, because many of the same ideas kept recurring. Okay, so that's the table of content. Now go to page 1, and on page 1, I got to explain, of course, what satisfiability is all about. So the question is something satisfiable or not? And satisfiable means that we have a Boolean formula, and the variables are either true or false, or 0 and 1, if equivalently. So we say true is 1 and false is 0. And we can always express any Boolean formula as an and of ors. So then the question is, can we find values of the variables that will make it evaluate to true, or in other words, evaluate to 1. So here I have an example formula, and can you see my mouse there? So f is this formula, and there's 3 variables, and of ors. So the first each thing that you're adding together is called a clause. So the first clause is x1 or x2 bar. That means either x1 is true or x2 is false. The second clause is it says either x2 or x3 is true. The third clause says either x1 is false or x3 is false, and the last clause says has 3 conditions: not x1 or not x2 or x3. Now, all these clauses are satisfied when x1, x2, x3 is 0, 0, 1. For example, x2 is 0, so that satisfies this guy, the first clause, and it satisfies the last clause too. Now, so we got to now to satisfy the next clause. Well, x3 is 1, so we got x2 or x3, and then x1 is 0, so we got this one too. So all 4 are fine. On the other hand, suppose we insist that you're not allowed to use 0, 0, 1. That means that you add another clause that says either x1 is 1, or x2 is 1, or x3 is 0. So then you can't have 0, 0, 1. So now we add this clause number 5 to the thing, and we get a formula that's unsatisfiable. There is no way to satisfy that one. Okay, so that's the problem with satisfiability. Now I now fast forward to page 3, where we use De Morgan's famous laws, which says that if we take the complement of a Boolean formula, we change and to or and or to and we complement every variable. So here's the same thing, but now the clauses have become instead, what do I call them? I forget. Let's see. Terms, I think I call them anyway. So a term. This says x1 is false and x2 is false. Or we have this. So we have an or of 4 terms here, and the complement function is unsatisfiable if and only if the original function is unsatisfiable if and only if it's identically 0, and that's if and only if its complement is identically 1. And that is, and a Boolean function that's identically 1 is called a tautology. Okay, so this is something always true, and that's an old word, tautology, which I did hear about when I was an undergraduate student. So people years ago talked about tautology, but they didn't talk about satisfiability. Now, so the tautology and the satisfiability are related by one being the complement of the other. So here's the prevailing view of mathematicians that was stated by Val Quine in 1940, but also, when I was an undergraduate in the early 60s, this was the same thing that was taught to me when I learned about tautologies, and it said that the whole problem of deciding whether something is a tautology is trivial. There's nothing to it, because all you have to do is check every case and make sure that it comes out true in every case. So in finitely many steps, you've got it. So people, in those days, distinguished between solvable problems and unsolvable problems. An unsolvable problem was something that, no matter how you might have to go infinitely many steps before you got to the answer. A solvable problem was something that you could say, I know I'd be able to stop and get the answer. and of course, and you know, Turing got famous for the halting problem, showing that that was an unsolvable problem. So the tautology problem is solvable, and finally many steps. So all you have to do is form a truth table in the normal way and check that you get true in every case. Now, in 1960, a paper came out in the ACM Journal that was not at all famous at the time, but it has become famous afterwards, by Martin Davis and Hilary Putnam. I guess I could mention that Dr. Putnam died earlier this year, and in the same year, 1960, he published another paper, which is the one that he's most known for. But anyway, this is other aspects of logic. But this is some work that they did as a consultant to, of all things, the National Security Agency, where they had some idea that there might be some interest in what turned out to be satisfiability, but only in they were trying to see if you could decide whether a formula is a tautology, and the abstract isn't going to mention anything about satisfiability. Now, however, they came across the problem as they were trying to solve a problem with quantified Boolean formulas, not just a simple Boolean formula, but a formula that has saying that something is true for all x and so on, and it also has functional symbols in it. So for all functions, they were working on a higher level problem and converting it to by logic to something that becomes equivalent. Essentially satisfiable. A couple of years later, 1962, was the publication in the Communication of the ACM. That was in the days when Communication of the ACM had a lot of research results. And this is work that was done at NYU by Martin Davis again, and then George Logelman, Don Loveland. And it used an idea that also Hilary Putnam had expressed in some previous preprints. So the program that's described here has become known as the DPLL algorithm, or Davis, Putnam, Logelman, Loveland algorithm, the original paper, 1960, talked about how to solve a problem by hand, well, I can't help mentioning here because I see Ailey in the front row, and I didn't put this, but I haven't really put this in print. But if you look at that paper today and look carefully at it, there's a way to do it by hand in sort of one line. And they spent several pages, but there's a way that they could have looked at their problem and never even discovered this algorithm and never even gotten around to writing this computer program. But anyway, they did program the IBM 74 computer at Columbia, and it was a heroic thing to do this program in 1962 because the machine had such a small memory. In order to solve this problem with backtracking, what they had to do is every level of the search tree, if you had to split that into two levels to be searched, they had to write it out onto magnetic tape, and so that they could read it in again when they were reconsidering a previous problem. So they had to shoehorn this all into a very small memory, and unfortunately the source code for the program has been forever lost, so we don't know exactly what the program did or can do it. But anyway, this turned out to be later on used enough that it got the name DPLL algorithm. Now, a big change occurred when Stephen Cook discovered the concept of NP completeness, and and here's his famous paper, which was, what was it, 1971, I think. Yeah, and his paper is called "The Complexity of Theorem Proving Procedures," and he doesn't talk about SAT in his summary. He talks about tautologies because that's what the audience would understand at that time. Not satisfiability, but what he shows is that if you can solve the satisfiability problem, you can solve almost every problem that anybody's interested in at the time. Any problem that we now call a problem in the class NP. So after this, satisfiability became the poster child for NP complete problems. It said if you can solve satisfiability with an efficient algorithm, then all these other problems, like the Hamiltonian path problem I talked about yesterday, and many other coloring problems and all these things, can be also done efficiently. So at this point, 1971, there was a heady optimism prevailing because all of the previous ideas about how long it took to solve certain problems were becoming overcome. For example, everybody used to think that matrix multiplication n by n matrices would take n cubed steps, but Strawson showed you could do it in n to the 2.7 steps. Algorithms that used to take n squared time, people were showing they could be done, a lot of them, in n log n time. Other algorithms that used to take n log n were like median finding or something like that. People found a way to do that in linear time. And so these barriers were falling right and left. And so here comes a new theorem that says all we have to do is solve this satisfiability problem, which seems pretty trivial. Just find it. Just find a combination of zeros and ones, and in fact, if you look at any satisfiability problem that you can write down in this on a page, you can solve it by hand quite quickly. There aren't any short satisfiability problems that are difficult. So it looked like for a few months it looked like that we were going to have a big breakthrough and knock off a whole huge bunch of problems at once. Of course, most of you know that this is now $1 million question, well, I don't want, in the questions we might get into the question is whether or not P equals NP, but I'm not going to do that today. I'm going to talk about SAT-solver, what we do know how to do. So Steve Cook's paper was revolutionary in bringing satisfiability to the forefront as a good problem to work on. And in fact, then he also developed a new algorithm for satisfiability, which he presented to his class in Toronto. I guess I can enlarge it here. This is, I found this in a thesis from Cornell that was published later in '72. And so he had a method I, or method 1, but I call it I, which was completely different from the DPL, from the Davis and Putnam approach, and it's a very elegant method, which you can read about in my book. But the main idea was that it gradually learned new clauses. So we start out with a whole bunch of clauses, and we will say those are satisfiable. And he says, well, if these clauses are satisfiable, so is this clause. And so we add more things that get to the thing. Now, this was very hard to imagine, though, how to store all these new clauses in the machine, and maybe if you should throw some away or something. So this method died and remained in obscurity. Was never published. And I just happened to notice because he anticipated some of the breakthroughs that were going to occur decades later. Okay, now I'm trying to get to the next page, which I will soon do after I learn how to use this browser. Okay, now there was another unseen breakthrough in 1982 that occurred in a journal, IEEE journal called Pattern Matching and Machine Intelligence or something, not too much read by computer scientist community, which if not in the abstract, but if you look at the methods inside, it introduced a new data structure technique to working on problems of this kind, and it's what we now call the idea of having watch list. So that when you have a data structure that, and it's we now call it a lazy data structure. So when we learn something new about the problem, instead of updating everything in the data structure, we just update the minimum that we have to. So with each clause we have a watch list, or with each variable we have a watch list saying if this variable changes, then update things that apply to this variable. But instead of looking through and updating all clauses, if we have a clause where we already know that it's satisfied, then we don't have to update it when any of the other variables in that clause changes. So anyway, they introduced this idea of a lazy data structure as a nice way when they were working on satisfiability problems. They kept only one watched variable in each clause, but a big breakthrough came in later when somebody said, "Oh, but we can keep two watch literals," and that turned out to be surprisingly much better than watching one, and watching three wouldn't do any good at all. So now I'm trying to give you the feeling, you know. I'm writing The Art of Computer Programming, and these things are going on, but I'm still not thinking of putting 300 pages in The Art of Computer Programming. In fact, you know, I'm thinking maybe having an exercise or two talking about satisfiability. And an interesting example of backtracking. And in fact, that's the way people viewed this, as saying, well, here's a problem where backtracking is a method where we sort of want to try a lot of possibilities and trial and error, you know, and if something doesn't work, try again. And satisfiability is one of the cleanest examples of a problem where we want to use backtracking. So people sort of used it as a test case of ideas that might apply to backtracking in general. But it was a curiosity. It was on the back burner, and every once in a while somebody would play around with it. But then there was this big breakthrough about the turn of the century, when three independent groups of people pretty much came up with very similar ideas about how to greatly improve the search for satisfiability. Two of these groups won this prize. I don't think that was well known about the others, but and so there were two groups. One was at Princeton, one was in Michigan, and let's see, actually, okay, so this write-up comes from Notices of the American Math Society, and it was written by Randy Bryant, who dean of the computer science school at CMU, and Randy was the principal for the BDD revolution 15 years earlier, the decision diagram data structure for Boolean function. And so I just, you know, so I spent, I wrote up about decision diagrams in volume 4A, And so then I saw this award going on. And I saw, oh yeah, there's a lot going on here, and sat there. I'll have to learn about that. I'll have to put that into Art of Computer Program, because it looks like here's something now we can solve problems that were considered to be impossible before this. So I wrote to Randy and said, who should be the person, the people that I should talk to learn all about this subject. And fortunately, I was, I got introduced to the principals, and they even invited me to give a talk about what I was hoping to learn for the Art of Computer Programming at one of their conferences. And so I got to make friends with all these guys. Now I want to show you some of the combinatorial problems on which satisfiability works out. Some of the more fun ones. There are in my book I have 100 example problems that cover quite a wide variety, and I try a lot of different methods on each of these problems. But one of the first ones is this. It is associated with the April Fool joke that Martin Gardner came up with in 1975. Martin Gardner's column in April in Scientific American in April '75 talked about 5 revolutionary things that had happened during the past year, and a lot of people believed that these 5 things had happened. I mean, not only was it, here's a map which needs 5 colors to. You can't. The 4-color theorem was found to be false because this map needed 5 colors to be colored, and this is called the McGregor graph. I added a parameter to it, so this is the McGregor graph of order 10. It's not too hard to generalize this to other order. But other things that were true is that e to the power pi times the square root of 163 is an integer. It turns out if you evaluate that with to 20 decimals, it's an integer plus zeros, very close. Ramanujan knew that. Okay, then pawn to king rook 4 is a winning first move in chess. The theory of special relativity is fatally flawed. Leonardo da Vinci invented the flush toilet, and Robert Ripoff devised a motor that is powered entirely by psychic energy. So this is the Ripoff motor, of course. Okay, so people didn't even realize that Ripoff was not a real name. Okay, but anyway, so this became a famous thing. There were paper in math journals proving that actually you could color this with four colors, so just in order to set the record straight. Okay, now I bring this up because graph coloring is one of the most natural things to set up as a satisfiability problem. For example, to have 4 colors, let's say red, green, blue, and white. And so I can have a Boolean variable that says the region 0, 0 is red, and so another variable, the region 0, 0 is blue, and so on. So one of the clauses is region 0, 0 is red or white or blue or green, and then I also have to have a clause that's saying I don't have both region 0, 0 is red and region 0, 1 is red, because that would violate the 4-color constraint, because 0, 0, and 0, 1 are next to each other. Okay, so those are the only clauses you need, and so is that satisfiable or not? Then then you can do it with 4 colors. So Randy Bryant came up with this diagram on the left here, showing let's see, can I, well, I was going to cover up the right diagram. I don't know, easy way to do it. So anyway, look at the one on the left. Not only can you color it with 4 colors, but you can do it with, one of the colors is only used 7 times. Blue is used only 7 times. This big region at the top looks pretty big, but it's only one region. So you need to, And that's pretty hard to do because there were 110 regions, and so you expect that it would be hard to do it because this graph isn't that easy to color with 4 colors. In fact, with the SAT solver. Randy found this with the SAT solver, and he also proved that 6 you can do it with 6. And you could also put in a few more clauses saying that the number of blue guys is only 6 at most, and that turns out to be unsatisfying. So on the right-hand side, I changed the condition a little bit, and I found that here's a way that to prove that there are more than 8 million ways to color this supposedly hard graph. With 4 colors, because each of these checkered regions could be either red or blue, and it would work. And there's 23 of those regions, so 2 to the 23rd, you can choose either red or blue in each of those, and you get a different solution. Now, but it turns out to be not at all easy to count the total number of ways to 4-color the migrator graph, and it's 898 trillion and so. Now, here's another coloring problem that's nice for example of a coloring problem. We try to put queens on a board so that no queens of the same color can attack each other. And here I've got 9 colors, not 8. It's impossible to do that with 8 colors of queens. But this is essentially the most balanced solution because there are 8 white queens, but then there are 7 of each of the other colors. The first row doesn't have a black queen. The second row doesn't have a light green queen or something like that, or red. Anyway, each row, each of the other rows misses one of the queens of one of the 8 colors. And so, it's not too it's not easy to find such a solution, but the SAT solver finds it very quickly. Here's another. Since we are talking about von Neumann lecture today, I think the previous von Neumann lecturer was John Conway. And so here's something that is related also to Martin Gardner's column, because John wrote about the game of life to Martin, and Martin put it in his column, and it became maybe the most popular column that Martin ever wrote. Now, how many people have never heard of the game of life before? Not you did. That's good. So I'm going to explain it to you. So, how many people have heard of the game of life? How many people that aren't listening? No, So the rule is that in this, there's a universe that consists of cells in a grid, and they're either black or white. White means they're dead, and black means they're alive. Now, a live cell stays alive at the next generation only in its following cases, that 2 or 3 of its neighbors are also alive. So every cell has 8 neighbors around it. And so if you have 2 or 3, if you're black and you got 2 or 3 black neighbors, then you stay alive, and at the next instant of time, you stay the same. On the other hand, if you've got 4 neighbors that are alive, or 5 or more than 3, then you die because of overcrowding. On the other hand, if you have less than 2 neighbors, then you die because of starvation. So you need some neighbors to support you, but but not too many, because otherwise it's bad for the world. So we have to have ethnic cleansing or something. So on the other hand, what about coming to life? So a cell that's dead has exactly 3 neighbors that are alive. Then it becomes live at the next step. So these are Conway's rules, and it turned out that he came up with this delicate balance thing where he started out actually trying to devise a system for artificial life that had that had, instead of just 2 states, it had 3. It had dead and male alive and female alive, and he was trying to, you have some rules that had something to do with copulation. But it turned out there was no simple rule for that, but he found this very lovely one that had only 2 states in each one. So now let's take a look at this, for example. In the upper left corner, it's dead. And it has 3 dead neighbors, so certainly it's going to be dead at the next time. Okay, but and look at all these groups of size 2. They're going to die because they have only one person supporting. Now there's a Z-shaped group that they're in the upper middle, and the guy in the middle is going to die because he's surrounded by 4. That's overcrowding. But the others are going to stay alive because they're supported by 3. So some people are going to be alive here. You can look at take a look at the one in the second row of the second column. It's got 3 neighbors that are alive, so that's going to come alive. Okay, so here's the answer. Check it out. Well, okay. All right. Now, so I found this with a SAT solver. It's pretty easy to set this up as clauses, saying, I have a Boolean variable. I want to make an example for my talk that ends with LIFE. And so I just set up a Boolean variable saying, should this be alive or not? And I wanted to fit in. I wanted to fit in this 7 by 15, I think it is, grid. And so I just have certain conditions as to how many neighbors it's supposed to have, and those are easily expressed as clauses. Okay. So now, actually, we can go further, and we can now ask for something that is there a predecessor to the guy on the top? Well, there isn't, except unless you go to a larger grid. But on the other hand, you can come up with a 2-step solution. Now, the particular solution that I have here at the left here, in the first example, uses the smallest number of black cells. I mean, there are many ways to do it. For example, this is one of the solutions, but it has more black cells than this guy. So with the fewest number of things alive, come to this. And when you have a problem in satisfiability, you can also add a few more clauses and saying, by the way, try to use at most 25 or say things that are alive, and then maybe you try also 24, and that turns out to be unsatisfiable. So with satisfiable, we can set the problem up easily, and the SAT solver not only solves this problem, but it almost instantly. Okay, so it comes out of the machine, by the time you hit character return. So I got this two-step solution. Yeah, look at that. You can also go another step, but it's impossible to have to do one more unless I use a larger grid. Okay, so that's another kind of example of satisfiability. Another problem related to the game of life is called the Garden of Eden configuration. The Garden of Eden configuration is something that has no predecessor. Nothing precedes it, and Conway proved that there exists a Garden of Eden configuration with something like 5 million on each side. There was at least one, and then people were finding smaller and smaller ones over the years. But about 3 years ago, using SAT solvers, people found what is now the smallest known example of a Garden of Eden. This is not known to be the smallest. That's a very difficult problem. But in this configuration, if you have any pattern whatsoever, according to the rules of the game of life, that includes black cells where it's black here and white cells where it's white here, but gray, where it's gray, you can have anything you want, and outside the diagram you can have anything you want. Then there's no predecessor. This is a Garden of Eden configuration, and it was and it was discovered using sat solver in a nice, clever way, and I think it took a few hours to do that one. Now here's my favorite, my personal favorite thing about the game of life is what sometimes called a flip-flop, or mobile flip-flop. Anyway, it's a pattern that this is a pattern that was invented by Bill Gosper at MIT about 1971, and it's called the Phoenix. And the reason it's called the Phoenix is that if you look at that every black cell dies at the next unit of time, but you get another Phoenix. I'll go back. This is the Phoenix. All the black cells become white, but now some others have come to life, and they again are going to die because it's a mirror image of the other one. Okay, so here we go. Isn't that something? Now, this is a very tight constraint. I've showed here both things on one screen. So all the tan cells are going to die, which means that they do not have 2 or 3 tan neighbors. They have either fewer than 2, or in fact, it's always fewer. They're always going to die of starvation. On the other hand, all the blue cells, the same thing, but all the tan cells have exactly 3 blue neighbors, because they have to come to life again when the blue guys are alive, and all the white cells have to remain dead, so they cannot have three tan neighbors, nor can they have 3 blue neighbors. So it's a very tightly constrained pattern, and the Phoenix. It's the smallest, this 8x8 thing, and I knew that there was also a pattern of something like 8x15. That's kind of a trivial modification of it. But I didn't know that there was any interesting flip-flops. I mean, Gosper had constructed a kind of a big one that's shown in John Conway's book. But it still had a very rigid geometrical structure. So I thought that this was pretty hard to do, but it was also easy to set up in SAT to say, find me a mobile flip-flop on a big board. And this is humanly impossible. I mean, it's really hard to find these patterns because of tight constraints on the balloon board. But lo and behold, I found that not only are there lots of solutions, but that you can find solutions that don't look geometrically rigid and they look kind of organic. And so there are lots of forbidden patterns, but it turned out that this illustration shows a lot of the flexibility that surprisingly is possible. So this is a Phoenix. It goes, I'm sorry, back and forth. Each thing dies and comes back together. So I'm recommending that if somebody wants to build a room for hackers to work, that they use this in the tiling of the floor. In fact, there is a hacker. What's it called? The hacker dojo in Silicon Valley, and the guy promised that he was going to do that. So I mean, because you can't hack all the time. Every once in a while you look and see, oh yeah, what a wonderful pattern here we have of these tiles that satisfy these magic constraints. Okay, now I've been talking at the high level and showing you some of the examples of the kinds of problems that are easily set up as satisfiability problems. Now I got to go dive to the low level and say, well, how do we actually solve it? Not I'm going to tell you that we can solve it, but I want to tell you something about how it's done. And so as I was writing this section, I programmed lots and lots of SAT solvers in order to, I can't write about something unless I tried to teach it to a computer. It's very hard to teach something. It's much better if you can teach something to a computer, then you understand it well enough to explain it to a person. It's much better. Okay, so I wrote about a dozen of them, and 7 of them appear in the book. Different kinds of solvers. Some of them are very easy to to express in code, and others are well, not. It took me a few months to get them written and debugged properly, and I put them I put them all on the web for people to experiment with. They're all expressed in what I call literate programming style, which I think is the best way to present a program that can be read by somebody else to figure out what it does, not just run. The first of these SAT solvers is I call it SAT 0. This is a kind of a 0 level. Does the obvious thing, backtracking, and if we look at it has 46 sections of code, and then I have well, here I have. I don't want to dwell on this, but just to give you an example of what I mean by literate programming, you combine. It's a combination of text language and C language. So I write a program that alternates between English and computer language, and so the introduction is in English, of course, and then it defines the format of the data, and so I give an example of how I express the clauses of the satisfiability problem, and then. When you get to writing a literate program, then you write it as a series of short sections, snippets of code, in which you're supposed to insert other snippets of code. So, for example, here it says you start out with the main program. It's preceded by declarations of variables and so on. Then it says process the command line, and that's section 4. And after you've done that, you initialize everything, that's section 8, and input the clauses, and then maybe report to the user what that you've got it, and so on. So you stuff in other sections, and when you're writing a literate program, you have a complicated final program made up of simple parts that are put together in simple ways. And so I think it's the best way. I mean, it's not only the best way; it's so much better than the second best way that I love it. My wife will tell you that I come out of my office several times a week saying literate programming is such fun. So, I don't know. So far in 2016, I've written about 200 of the little programs, some of which are longer, some are short. Okay, now. In the book, I have 7 examples of algorithms for SAT solving, and algorithm A was what corresponded to that SAT 0. Algorithm B is another version that uses this idea of lazy data structures that I talked about, having a watch list, and it's amazingly lightweight code. It doesn't take much space in the computer, and it runs faster than algorithm A. And so anyway, it's a nice thing. So that program is online as SAT0W. The W stands for watch list. There are many ways to approach the satisfiability problem, and one of the ones that people like is based on randomization. And it's called WalkSat. It does a random walk. So you start out with some pattern of truths and falses, and then maybe it doesn't satisfy. So you find something that looks like maybe if I change this from true to false or the other way, maybe now it'll be satisfied. And so you change one of them, and you take a little walk, and then you see, and then you look, okay, satisfied now, oh, no, maybe I'll try this one. So you do a walk around, and if it's satisfiable, maybe you're going to get the answer. And it sounds like it might be hopeless, but in fact, often it works beautifully. And so there's lots of problems for which this is the method of choice. Not for an unsatisfiable problem. Random's walk will go forever, and it gives you no indication that there's going to be anything else. Another method is based on message passing, and this is invented by physicists who are studying interesting processes of statistical mechanics, and this works beautifully on random problems that are a million variables or more, if they're satisfiable. But it doesn't work at all on combinatorial problems, and nobody knows how to beef it up for that kind of problem. But for the random problems, if you actually have one, this physicist method is extremely interesting. So the random formulas are written up in Siam News 10 years ago. Now there's sort of the standard DPLL method. That's the 1962 method, but brought up a little bit to date. Is another one of the solvers in my book, and then comes one of the two major solvers, sort of the state of the art. Now, every year there's a competition, international competition, a very fierce competition to find to solve a big abray of benchmarks as fast as you can, and different kinds of benchmarks, and there are two main streams of SAT solvers for these benchmarks. The one is called the look-ahead solver, and the other is called a solver based on learning of clauses. But SAT 11 is an example of a state-of-the-art. State-of-the-art as of 3 years ago, a look-ahead solver. And the idea in look-ahead solver is before you choose something to branch on, spend a lot of time figuring out what might be good by doing a little bit of experiment, saying if I branch on X13, is anything nice gonna show up? And if I try that for all the variables, maybe there's something that's pretty close to a breakthrough. And so, but we're looking ahead on a fair number of problems, maybe 10% of problems. The look-ahead solver does extremely well. But the main workhorse for the 90% is represented by this program SAT 13 I have on the web. And it's called CDCL solver which is constraint-driven clause learning, and this is really the thing that caused the breakthrough in the year 2000. How to decide clauses that to add to the ones you have and learn those and then gradually cut down the search space more and more so that you can find a needle in a haystack. I also have a preprocessor. I won't talk about that today. Now, what happened here? Page 38. Why am I not seeing this page? Oh, okay. I don't know what happened here. The preview. Is it two? So here's the example I gave long ago from page 1, and just to show you how I input it to the solvers that are online. You can easily install any of these programs and play with them. And so that had 4 clauses. So I have 4 lines here showing the clauses, and you can have comment if you start with with this character. Then you can give comment to ignore it. So here's and then add this extra clause and get the unsolvable problem. So that's the input format. Now, I want to talk about a particular problem and give you some insight for how the process might work. So let's try to solve a non-trivial satisfiability problem. So consider the following. I've got red and blue balls. I got eight of them all together, and no three balls of the same color are equally spaced. No three red and equally spaced, no three blue. So for example, here, incorrect would be this first one here, which has three reds that are equally spaced. And here's, again, three reds equally spaced. This time the spacing is, there's one ball between them. So this is no good, this is no good, and this one is no good either because it has three blue balls equally spaced. Okay, so good. Those are the bad ones. Let's try to see if we can find a solution to this problem. So go on. Okay, come back. I'm sorry, I have to. So we start out at the beginning. We have 8 question marks, and now we have to. So let's look at the left one and see. It's going to be either blue or red. So here's the case where I make the left guy blue, and they're making, I don't know why I lit up, make the left guy blue, and then the other case is going to be symmetrical to it, just changing the color. Okay, so now suppose we go then and check the second guy, and it can be either blue or red. So let's consider what, if I make the second guy blue also, then I'm forced to make the third one red, otherwise I got 3 blues in a row. Okay, so that guy's red. Now what am I? Now I have 2 choices, and one of them is blue, and one is red. Go to the next page, and similar we have this branch. Okay, so time for the next page. Okay, so 8 balls. Continue. So I had these 2 branches. Well, we don't have time to go through the details, but at the bottom line here. In this blue case, there were 2 forcing me. This blue and this blue force, this got to be red. This blue and this blue force, this got to be red. So I have 2 reds here, and that's going to force blues, and I'm in trouble. So this thing dies out. On the other hand, this branch, there are things that are forced, and all of a sudden, yes, I got a solution. So hooray! No 3 equally spaced of the same color. And there are 2 other solutions here, and then on the other half of the tree, there will be 3 more. So we get 6 solutions altogether. So that's the solution to that problem. And now let me show you that. Then I also online I have an example then of a generator for this Van der Waerden. It's called the Van der Waerden problem. I don't want to go into the detail, but Van der Waerden proved famous theorem that said that there will be such there's a limit on how many balls you can place without making it unsatisfiable. So Saint-Waerden 338 says that I want no 3 red equally spaced, no 3 blue equally spaced, and 8 balls altogether, and that generates these clauses here. So first clause is 1, 2, 3. It says I can't have one. To say the variable is true means it's red. So I can't have 1, 2, and 3 red. I'm sorry. I can't have one. I have to have 1, 2, or 3 red. Because they couldn't all be blue, and so I have to have either 2, 3, or 4, and similarly the complements. So these are the clauses that we have to decide satisfiability, and by hand we worked it out that there are 6 solutions to that. Now, what if we feed that in then to our SAT solvers? So here I take this input and I pipe it into SAT0 solver, which was the easiest one. And so it says 8 variables, 24 clauses, 72 literals altogether, and it was satisfiable. And so it gives an example how we satisfy it. And the total running time is reported here. It said 8, well, what is it? I can't read it. 850 plus 384 MEMS. Now, MEMS In my book, I don't report running time of a program in seconds. I report it in MEMS, which are references to memory. The reason is, I think that you probably can guess that if you read any paper that was written 10 years ago, and it tells you how many seconds it took to run a program, you know that that has absolutely no meaning anymore because nobody remembers how fast those machines were. And and every year goes by, it gets less and less meaningful. But the number of memory references stays the same, and it becomes it's more or less not a bad approximation to the running time. So I report the running time in MEMS. The first time was how much time it was to read in the data, 850 MEMS to read, and then 384. This was just initializing my data stream. And then once I got going, it took me only 384 references to memory to find a solution to that problem that we did by, of course, we did it by hand. There was 0 references to memory, except we had to use our own memory. Okay, now next let's try with 9 balls instead of 8. So in this case, 9 variables, 32 clauses, and it's unsat. So that one is unsatisfiable, and in order to prove that, it took 1,000 MEMS to read it in and 9,000 to carry out the exhaustive enumeration of all cases. So then I go into SAS 0W, which is the one that has these watch lists. And it turns out, well, that uses only, it goes 3 times faster. It only uses 80 bytes of memory as well. So it actually had a search tree of 79 nodes instead of 75 to prove unsatisfiability. But its inner loop was much faster because of these watch lists. So this is an example of the kind of things that you can play around with. And so I also, let's plug it into the DPLL solver, and that one takes 5,000 MEMS instead of 3,000 with the watch list. Here's the look-ahead solver. That one is 9,000 MEMS, and then the last one, which is the clause learning solver, was the winner. It took less than 3,000 MEMS for the calculation. Now now it also writes here at the bottom, it says 6 learned clauses written to a file, temp learned. So it's going to prove unsatisfiability by learning new clauses that are added to the original. And this is interesting. This is the key to the idea of clause learning. So I want to go through it, even though I'm already spoken for almost an hour. So he says, no, but you're being too generous because you don't know how long I'm going to go over. But I definitely want to. But I definitely want to show you this guy. Okay, so here's. These are the 6 clauses that it learned, and it learns them one at a time. The first clause it learned was not 3 or not 5. The next clause it learned was either 4 or not 5. And so I'm going to examine now the first of these, not 3 or not 5. So it concluded after this problem of 9 balls, no 3 equally spaced of the same color, that you can't have 3 and 5 both red. And so what's the proof? Okay, suppose 3 and 5 are both red. Well, then we have to put a blue in between them. We also have to put a blue over here, and we have to put a blue over here, because otherwise we have 3 blue. Okay, so then we got 3 blues that are equally spaced. Too bad. So we've learned that. Okay, now now the next clause that we learn is 4 or not 5. So let's see why are we justifying in learning that? I'm sorry, I can't get to the next slide. There we go. Okay, so we verified that the first one is validly learned. And in fact, this is the idea that every time you learn a clause, it means that if you add the negation of the clause, you immediately get to a contradiction without thinking ahead, without just sort of, but by forced moves, you're going to get to a contradiction. So let's try the 4, not 5. That means that if it's not true, we're going to have a blue one in position 4 and a red one in position 5. So what happens there? Well, that forces a blue one. That forces a blue one here, because we know that we can't have 2 reds. We've already proved that we can't have 3 and 5 both red. So we now force, because of the previous clause we learned, we've now forced this guy to be blue. But that forces a red one here, and that forces a blue one here, and that forces a red one here, and that forces a blue one here, and so on. And we get a contradiction. So again, we're allowed to learn that clause, and so we checked off the first 2. And similarly, now we try to set 5 equal to red, and we find that because of the other things we've learned, that's going to force a contradiction, and eventually we're going to get to a situation where we get a contradiction off the bat. So that's it. That's the idea of learning clauses. The computer figures out clauses that could be that are true because their denial is easily shown to be wrong. Okay. Now let's go to harder problems. So now we're going to have 34 balls, and we don't want any 4 to be equally spaced. And so we send this to our set our set solver. It takes 100 and some thousand mems. That's a fraction of a second, fraction of a millisecond nowadays. But 134. It finds a solution. And on the other hand, if we try for 35 balls and no 4 in a row, that's unsatisfiable, and it takes 500,000 mems to do that. And I didn't write down here how many clauses it learned, but I should have. Now, wait, yeah, was that set 13? Yeah, that's set 13. Oh no, yeah. Now I'm going to 5 things equally spaced. Now it's getting more of a challenge. We got 177 Boolean variables, and 2 to the 177 is a fairly large number, if we're going to do trial and error. But it solves this. It finds a solution after 74 million mems, but then we try to go to 178. And here it took what? Let's see. This is a million. This is 21 billion mems, which on my machine was 1 minute and 15 seconds. And it found about 900,000 clauses that it learned in the process of doing it. But actually, this, if somebody challenges you and says, okay, you said it's unsatisfiable, but how, can I trust you? What if you had a bug in your program? You just said there's no answer, but why should I believe you? And so you can look at those learned clauses, and a very simple program, completely independent of my program, can look at those learned clauses and check each one, showing that each one each one is valid to be learned in view of the ones that have previously been learned. So you also have a proof of unsatisfiability here. Next problem is related to the handout that you got. Did everybody have a sheet of paper that has a little puzzle on it? Because that's what I want to talk about next. This is another application of SET to what's called digital tomography. I give you how many black pixels there are in each row, and I give you how many black pixels there are in each column, and I also give you, for each diagonal, I give you how many black pixels there are in that diagonal and how many in this diagonal. So you try to, so the question is, erase the picture in the middle. Is there a solution to these counts? And when I pose this problem, I I thought maybe there wouldn't be that many solutions to it. Because there's a little bit of information theory saying what's the chance of having these sums and so on, but there's a lot of correlations there, so it's hard to figure out how many. Well, it turned out that that this problem shows the limitations of satisfiability because in this particular problem, the method of choice is not to use a SAT solver, but the method of choice is to use something that people in OR have been developing for 50 years, and that's called integer programming. And because all the constraints here are really based on arithmetic, and integer programming is very good at arithmetic. And SAT solvers, in order to do arithmetic, you have to program carrying and things like that in order to do plus and minus, and so they can't compete with 400 years of mathematics of developing linear algebra. It turned out that there were lots and lots of solutions to this problem, and here are three extreme examples of solutions. The first one is the one that's lexicographically, the one that's smallest. If you first have as many whites as you can until you find a need a black one, and the last one, on the one on the right, puts the black as far left as it can go and complete, and the one in the middle has the fewest pixels in common with the cat that I had, and in order to get the one in the middle. My programs for my SAT solvers were not getting the answer, but I wrote to my friends who had very good integer programming solvers, and they gave me the answer, in a second or two. So SAT solvers are great, but they aren't good for everything. On the other hand, if you take a problem like this and you add any other constraints that aren't easy to put into integer programming for them, then the SAT solver becomes good again. For example, instead of just saying how many ones are there in each row, I can say how many runs of ones are there too. I can say that there are five ones in this, but they only appear in two different runs. They're two clusters of it's either 1 and 4 or 2 and 3 or something like that. And then it turns out that the solution is unique, and the SAT solver finds it very, very fast, and the integer programming solver is not so great. So that's that. And now here's your puzzle. Okay, so the problem that I handed out is a digital tomography problem, but it's smaller than the cat problem, and it's one that you can actually do by hand. And in fact, I got to give a spoiler alert now here, because I'm going to tell you how to get started on this puzzle. So if you want to have all the fun of solving it yourself, you should now close your eyes and not listen for a minute, because I'm going to tell you the answer to the upper left corner. Okay, you're laughing. Okay, so in the upper left, the upper left corner has to be black. Now, the reason is that I gave you the number of ones on this diagonal. Okay. So anyway, the rest of them you can figure out. Now, actually, I recommend actually doing the upper right corner next to it. Yeah. Okay. Now, but here's the way a SAT solver would go to the problem. So I have another program on the web called SAT Tomography, and you can feed in a matrix of zeros and ones, and it will, a matrix of a series of row and column and diagonal sums, and then it will output a bunch of clauses, which are not real hard to understand, but it's encoded. But these clauses, I left some of them out at the bottom, but these clauses encode that very puzzle that you have in your hand, and you don't have to solve it now, my dear. You can. But of course, you're in biology, so it's okay for. So now, okay, so here then I did SAT tomography prep, and I used puzzle data, and then I pipe that into the SAT tomography problem, and then into my solver, SAT13, and what it does is it tells you that the problem had 1,039 variables and had 3,926 clauses, and the clauses weren't too long, and it's satisfiable. So there is an answer. And furthermore, it tells you that it took 31,000 MEMS to find the answer, but there were 0 nodes in the search tree. Now, 0 nodes in the search tree meant that it never had to make a guess. It didn't have to learn anything, but it could just go downhill, one step at a time. So in other words, I told you how to do the first step. There's always there's a second step. There's a third step where you don't have to guess. If you just find the right, you have to choose, at every step you have to choose one of the rows or columns or diagonals, but then there is one that's ready to go and has a forced answer. So that's that problem. But but when you get the answer, please don't tell the guy on your left or your right, because that'll spoil it for them. Because it's a fun answer. Anyway, it's not just a random. It's not a cat though. Okay, now this is now I get to the part of which is I think a lot of people are going to buy this book primarily for the 2 pages of illustrations that I'm going to show you a few of now. So anyway, it's a picture book not as well as a So a guy named Carsten Zins in Germany developed a really nice way to visualize the input to SAT problems. And what he does is he uses a ball, here's a purple ball, for each variable of the problem. And then he connects the balls by straw or something, some sticks, if they appear together in some clause of the problem. So if there is no connection between 2 balls, that means that they don't occur simultaneously. But although there might be something else that makes it a longer path. But anyway, this helps to visualize a little bit the input to one of these large problems where we have thousands of variables and lots of clauses. And then I want to show you these pictures just to give you some idea at the wide variety of problems that a SAT solver is faced with doing, as well as the wide variety of problems that we can present to a SAT solver. The point is, just as Steve Cook showed, that if you could solve the SAT problem, you could do lots and hundreds and thousands of other interesting problems. The reason is that Boolean algebra is so powerful that you can, as a modeling language, that you can model an incredibly number of different problems as satisfiability problems, and these illustrations give you some idea of the variety, because as you see there are gosh, I'm going to have to, okay, so that first one was something like the problem of the balls, equally spaced balls, not exactly, but a related problem. This problem is based on a circuit for multiplication and trying to find a test case that lights up a certain variable to see if the manufacturer has made one of the gates stuck at 0 or stuck at 1. People use that solvers to find test data for checking for manufacturing defects. This one is a let's see. I think this one. Was it coloring the McGregor graph? No, this is for finding a coloring of queens. So I showed you this problem of trying to find 9 coloring of queen. The next one is this is trying to four-color the McGregor graph, but using one color only 6 times instead of 7 times. And the next one is also for the McGregor graph, but using a different encoding of the constraint about 6. Changing those clauses gives quite a different problem to the SAT solver. This one is for optimal sorting network. It's a way to prove that the best way to sort 9 elements in parallel, it takes a certain number of comparisons. And this one is another example. This is from mutual exclusion protocol, and checking the validity of a certain method. So anyway, the idea is lots of different patterns come to SAT solvers. You can imagine why it might be better to have several kinds of SAT solvers, but also they have to be versatile and lots of other problems that have never been put to SAT solvers are undoubtedly going to be happening. Wait a minute, maybe this is the protocol one. Okay, now I got to go larger, and I want to show you a surprise that one of the surprises I got while writing this section was I used it to find a new circuit. Synthesizing a circuit means I have Boolean functions, and I want to find the smallest number of gates that will implement this function, and I'm using binary gates, so I have and, or, exclusive or, and also and not, or less than as predicates. So I used to, so the problem that I'm trying to solve here is called sideways addition. We have five Boolean numbers, 0 or 1, and we want to express the sum, which is either 0, 1, 2, 3, 4, or 5, and we can express it in binary notation. So we want to find Z2, Z1, Z0 that express the sum of the 5 x's. So that those are 3 Boolean functions depending on 5 Boolean variables. And when I wrote volume 4A, I had found a way to compute Z2, Z1, and Z0 with what I thought was an amazingly efficient scheme. In fact, so I asked the SAT solver essentially to prove that you couldn't do any better, and it found a better solution. And so here is the same problem now, but with one fewer gate in the solution. And the thing that's remarkable about it is that if you found that if you just took Z2 by itself and said what's the shortest thing that works for that one, it needs 10 gates, and I've used 10 gates here. Similarly for Z0, it needs 4 gates, and I've used here. So each of these is computed with the optimal number of gates, but they also, in a way that they share computations with the other ones and fit together. So it's way better than anything else. Okay, now to conclude, I have one more problem that I wanted to show you, because this was a breakthrough, happened earlier this year and got into some news groups and so on. It's called the problem of Pythagorean triples. So we have to take the number. Each number we color it either red or blue. So either 1 is either red or blue, 2 is either red or blue, and 3 and so on up to n. And each integer is colored either red or blue, but we're not allowed to have a Pythagorean triple, which means I'm not allowed to have A, B, and C all red if A squared plus B squared plus equals C squared. And they can't all be blue either. And so Ron Graham, in 1984, asked this question: is it possible to color all integers in this way? And he offered to pay $100 if you could prove or disprove that. Then in 2008, it was shown that you can get up to 1344 without having any Pythagorean triple. And in 2009, it got up to 1,500. And here's a type, in 2015, it got up to 6,500. So, you know, and then a few months later, it was raised up to 7,600. But now, in February of this year, using SatSolver, this won the best paper prize at the SANT conference this July. It said that yes, 7824 numbers up to 720 can be done with no Pythagorean triples, but 7825 no. And so this, so you know, so Ron of course paid off, but this shows that you can't go up to infinity, and not only that, but you have the exact place where it stops. And so this is the paper that they wrote that was, you know, the best paper at the conference. And I could just show you that the clauses are very simple. For this, you say that, you know, either 3 or 4 or 5. It means either 3 has to be red or 4 has to be red or 5 has to be red. Similarly, one of them has to be blue. And for all the Pythagorean triples, you just do that. Here I just went up to 7825 to show it. Okay, so now if I put it into my solver, but it only has to go up to 6,500, which was the record from 2 years ago, then I can get the answer in 12 minutes. And you know, about this many mems, about 1.4 teramems, and it has to learn a bunch of clauses, but getting past 6,500 is hard, and they went up to, remember, to 7,800. So they did this with the state-of-the-art SatSolver at the moment. And it took 35,000 hours of CPU time, and they divided the task into 1 million independent jobs to be run in parallel. And the interesting thing is that they used the look-ahead solver to divide into the 1 million subproblem, because the look-ahead solver is good for that. And then they used the clause learning solvers on the 1 million subproblems and did that in parallel. And the computation was completed in 2 days because they have a computer cluster there in Texas that did the calculation. So anyway, that's an example of state of the art. And you told me I could go half an hour over, so I did. Okay, thanks very much.
In such von Neumann lectures, we call this session Sweatbox session, which means tough questions about the lecture, about von Neumann, about open topics. So please go ahead. Who has a question?
Hi,
Please.
Professor Knuth. Thank you very much for your lecture, very insightful. I'm a second-year PhD student working with Paul Valiant on randomized algorithms, and my following question is on your perspective on the area, or really the field of theoretical computer science in general. Okay. And related to SAT and NP-complete problems. So the premise is that, and I think I'm quoting Professors Dick Lipton and Ken Reagan on their blog, they're saying that these days, our practical modern needs seem to be contradicting our traditional intuitions about complexity theory. So for example, these days, with very large problem instances, people are saying that quadratic algorithms are actually not practical. We need linear algorithms. Whereas if we could actually reduce it naturally to a SAT problem, feeding it into a SAT solver is actually way more practical than a quadratic algorithm. This seems to be contradicting, you know, the intuition that, you know, P is good and NP complete is bad. And it seems to suggest that complexity theory, you know, might not be asking the right questions. It might not be aligning with, you know, actual practical needs. So my question is, what do you think is the main values in resolving open complexity theoretic problems such as P equals NP or many other complexity classes? what's the mean value in that? Or should we be looking at finding better ways of talking about complexities of problems and algorithms?
Yeah, okay. Of course, that's a great question. It involves, the philosophy by which thousands of people live every day. So I have to say first that a little bit like I said yesterday, that I don't like to say that one area is definitely better than another, and so we should stop working on the other one. Just I gave the example of cancer as being not the only disease yesterday. I don't say that the pursuit of polynomial time algorithm has been a mistake. It's true that for many problems of big data, you need a linear algorithm instead of a quadratic algorithm. But there are still lots of algorithms that I'm interested in where n, doesn't get more than 100,000, and that's 10 to the 10th. I can do that in a couple of minutes if it's a quadratic. N squared isn't so bad, unless n gets real big. Though, on the other hand, there are algorithms where linear time isn't good enough, and you need sublinear algorithms, and if n is it get bigger. There's no general. I can't give you a general answer saying don't go for polynomial or the other, but I also have always felt that the way people interpret the question of polynomial versus non-polynomial time has been fatally flawed from the beginning, because suppose you have an algorithm that takes 2 to the n steps, and another algorithm that takes n to the 4th steps, or something. Anyway, or let's say 8 to the 10th steps for the heck of it. Okay, so you have a method that takes 2 to the n steps. You can at least solve that when n is 30. But end of the 10th or end of you can't solve that for any n, even though it's polynomial time. So, I had an algorithm. Okay, so I don't want to belabor that, but you have to know the coefficient, and you have to know if you're interested in large n or small n. I mean, for practical problems, because many practical problems are actually n isn't that big. N is always constrained by the size of the universe, and so there are many. There are many theoretical papers that introduce that save a factor of log n by greatly increasing the constant size. But you can do it in log n. You can do it in running time divided by log n, and so wow, we asymptotically better. But log n is never bigger than 5. I mean, if you have 2 to the 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 2, that's bigger than we're going to have. So n isn't going to be that big. So on the other hand, the papers that get out this extra factor of log n, I don't throw them out, because they identify bottlenecks and they show that certain things can't be shown impossible. And so there's value in that kind of theory as well. And all of these studies, furthermore, as we're working on these problems, we're developing our own intuition to reason about algorithms, and so we're able to tackle many more problems than if we didn't have that intuition. So it's not so much the actual results that are important to me, but the things we learn while working on a problem. That's my bottom line is knowledge. So I work on some problems that are absolutely pure, that I know have no practical significance whatsoever, because that sharpens the tools that I'm going to be using for other problems that I'm going to be interested in next week. So and there's more to it too then, because even in the old days when we didn't have P versus N people, we had only solvable versus unsolvable. People were saying, "Oh, don't work on this. It's unsolvable. So so it's hopeless. So work on something else." But the fact is that almost every problem that we've ever solved is a special case of some unsolvable problem. And I mean, take for example calculus. The problem, you have a function of n, and the question is the limit of f of n as n goes to infinity equal to 0 or not? Okay, now this is a fundamental problem in calculus, to decide whether a sequence that's defined by some definite rule converges to 0. And this is an unsolvable problem, because we can write down a formula, not too hard, that expresses f of n it says that a certain Turing machine is running at time n. And if the answer, so if the limit as n goes to infinity is 0, that solves the halting problem, which we know is unsolvable. So if we took the attitude that we shouldn't work on unsolvable problems, then we would never develop calculus. We would say, oh yeah, limit is 0, that's beyond us, so let's not look at it. So you have to realize that that all these problems that are hard in some sense complexity-wise also have special cases that aren't so hard. All right? So that's a sort of a rundown on the way people have distorted the significance of theory and saying that this is much better kind of research than this. I find a lot of value in almost all the research I look at. I could complain about a few things that I think are never going to lead anywhere, but I don't want to make any enemies. But there's a whole bunch of papers that are associated with the name Smarandash, and I'm sorry that he seems to be from Romania, but anyway, I've never found anything of the slightest interest in those. I guess it's going out on the internet now, so I'm going to make a lot of enemies.
Okay, I'll jump in with a question. So it's part of the legend that when you worked on the Knuth-Morris-Pratt algorithm, the linear time algorithm to find the pattern in a text, that you actually took Steve Cook's proof that two-way automata, push-down automata can be recognized the languages can be recognized in linear time, and so it's very interesting how very deep theoretical results could lead to practical algorithm optimal.
Yeah, okay, so this was, it's the way I discovered that algorithm, although Jim Morris discovered it in a completely different way. But anyway, but I also did similar things with other algorithms, so I might as well describe the story. So it's a matter of, okay, I thought of, okay, I learned this theorem of Steve Cook. Let me explain what the theorem says. There's a certain kind of automaton that has an interesting property that if you can write a program, if this automaton can solve a problem in any time, any finite time whatsoever, then you can write a program for a random access machine that solves that problem in linear time. So all you have to do is find a way to program this funny computer and not worry about that if you're taking if you're running for centuries, but as long as it's going to get the answer, then if you can figure out how to program that machine to do it, then you're in good shape because then a program on a real computer will be efficient. And so then I learned about a problem that you could solve on that machine, and it was not the pattern matching problem, but it was the palindrome star problem. So it says a palindrome is a binary string that is the same as its left-right reflection. And you wanted to recognize whether a given string, like you have maybe in biology, can be represented as a concatenation of palindromes. And so it was possible to write a program for Steve Cook's machine that recognized that class, and therefore there is a linear time way to check whether a given string is a concatenation of palindrome. Okay, so I considered myself a pretty good programmer, and I couldn't figure out any linear way to. I looked at this problem and I said, so, there's a way to do it, but how the heck can I do it? So so here was the first time in my life where automata theory hadn't just been sort of mildly interesting, but automata theory showed that something existed that I couldn't do with all my human brains, and so I looked a little further and I found another problem that's a little simpler than the palindrome problem that was namely to find whether one string was within another. And I programmed that for his machine, and that turned out to be like the pattern matching problem in a sense. And so for that the program for the machine was only about a dozen lines. So then I could look at Steve's proof, and I could see how he proved it. I only had to do a certain construction that he had in his paper, and I had a big blackboard, and I wrote it out, the complete solution. Okay, here's how the program does it, builds this table, and so in linear time I was supposed to be able to get it afterward. And after about an hour and a half, I'm filling out maybe 2 feet of the blackboard and so on, and all of a sudden, aha! There's what I didn't think of, and so that's the way I discovered the Knuth-Morse-Pratt algorithm.
Good. Other questions?
So you were talking a bit about, make it stop doing that, a bit about how sort of a lot of interesting problems are special cases of things that can't be solved. You also showed these, sort of visualizations of things. Once you crunch them into a SAT solver, they have these sort of pretty structures. They all look different. Is there any, has there been any work? Have you noticed anything just looking at these? It seems like encoding something in SAT and then looking at it might be a good way to find intuition about, certain problems in general are not solvable quickly, but under certain constraints might take on some symmetry or some clunkiness or some whatever.
Yeah. Okay, so if I knew a good answer to that, I would have put it in the book, and it would have been more than 300 pages. But I do talk a lot about symmetry in there, and I have a new approach to symmetry that goes beyond anything in the literature, because I describe it in terms of endomorphisms instead of automorphisms. What it means is that people discussing symmetry were considering reducing problems to others that are equivalent under an automorphism of the problem, the symmetry of the problem. But instead, I have an endomorphism where I have a homomorphism of the problem to another problem, and I observe that that you can simplify even better if you use that model. And I give a few examples of that on pages 105 or so, to 110 or something of that book. But there are some ideas there. But I really believe that that we're far from discovering what's known about satisfiability problem, and this idea of learning clauses made a sea change in the efficiency of the methods. Another method I didn't talk about in my talk is the idea of restarting. Every once in a while, throw out what you were working on, although remember what you've learned, but then start over again. And that's another idea that's important, that has been important to improve. But the fascinating thing about this is that when you're working with clauses, there's this principle of resolution that if you use a certain kind of resolution called tree resolution, it's equivalent to the DPLL type of SAT solver. But if you use extended resolution, okay, so there's a lot of great results in literature getting lower bounds saying that the shortest proof of unsatisfiability by tree resolution is long, and therefore DPL SAT solver could never do it. But there's another kind of resolution called extended resolution for which we have no lower bounds whatsoever. Try to simplify, using extended resolution is something like a mathematician saying, in order to prove this theorem, let me first prove this lemma. So it says, just take the clauses that you have and now introduce some new variables and some brand new clauses and add that to the problem. And that's not going to, but if you do it just saying that there exists either X or Y or Z is true, then certainly you haven't made it unsatisfiable. So you can add these extra things which amount to saying that a certain lemma is also true. And if that's provable, then there are ways to there are ways known in some problems to find a linear to find a linear size construction, although without the extended resolution you can't. And nobody has lower bounds for this, and so it might be that we're going to have a breakthrough next year where somebody says, not only do I have a way to learn clauses, but I can also have a way to suggest new lemmas based on the structure of the problem that somebody gave me. Okay, so there's lots of hope for other things in the future. My main message now, though, is for everybody to buy my book.
So I'm going to ask the obvious question now. So in terms of whether the whole thing can at some point be solved in polynomial time, what's your hunch?
Yeah, I believe that that P equals NP. That is, I have a feeling that if the problem is ever resolved, somebody will show that there exists, in fact, there does exist a polynomial time algorithm for SAT. On the other hand, I also predict that if this happens, it's not going to be good news for anybody, because the proof will only show that it exists. It won't give us a clue as to what to do. It won't even give us a clue as to what the order of the polynomial is. It'll just say that there is some integer, maybe 10 to the 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 10, so that there exists an algorithm that will finish every that problem of size n into that integer steps. But we don't know what the integer is. We don't even have. We're bound on the integer. We just know that it exists. So existence is a completely different problem for embodiment. And so every time you see a statement that says that, if P equals NP, then we're in good shape. I don't believe it, because you have to distinguish between existence of an algorithm and knowledge of an algorithm. There are lots of examples already that we have where we know that algorithms exist, but that we have no idea how to compute them. And one of the nicest of such examples is connected with the theory of graph minors. There's this beautiful theorem of Paul Seymour and Robinson, saying that if you have any family of graphs that's closed under taking of minors, which is a simple concept, then there exists a polynomial time algorithm to recognize graphs in this family. However, it gives us only in a few cases is this algorithm known. All we know is that there is some finite number of graphs that we have to check that aren't contained as minors in our given graph. And if we have a finite set, then there exists a polynomial time algorithm to check for these if any of these finite sets do, and that's the algorithm, and it's polynomial time. But we have no more information. So that's an algorithm that exists, and it's polynomial time, but we don't know it.
Other questions? Wow. There is another question.
Follow-up, since there's not some justification why you think that's going to be the case. That's one thing. And second, if we end up having an existence proof.
No, I understand that. A lot of people argue that P is probably unequal to NP because you've had all these really smart people working hard on it, and they haven't come up with an algorithm yet. My argument is the same. It says P is equal to NP because we've had all these people to try to prove that they're unequal, and they haven't come up with an argument.
But that would make you agnostic, no?
All right. So I once asked Erdos 2 questions, and I would like to see how your answers to those 2 questions.
Okay.
One was if complicated proofs for, let's say, d equals 2 exist, and you found them and you are trying d equals 3, which is the general case, typically complicated proofs simplify if they are horrendously difficult, so you can see the next generalization, or not. His answer was no. Some of them they are not going to be in the God's book just because they are complicated and so on.
Okay.
So I'm giving you the second one, and then I want your answers. So the second question was, when do you give up on a problem? How many decades you work? Are we bound ethically to solve it by the end of our lives and so on? So he was very frail, and he started all of a sudden becoming very active and shouted at me, "Never!" I worked on a problem and I solved it 20 years later. Once you work on it, your brain works on it, you don't know about this, so from time to time go back, you're going to solve it. How do you look at those?
Yeah, I agree. Paul stayed at our house a few times, and I know that he almost never slept, and so I don't want to recommend that you go to extremes. I mean, he took Benzedrine and so on in order so that he could solve more problems per unit time and stuff like that. So I put problems away. I said yesterday I send some of them to Richard Stanley, and I know life goes on, but Paul is right that it's also in the back of my mind. So at least 3 times in my life I had a problem where I worked on it really hard, and finally I decided, okay, no, if I don't get it by Monday, I'm going to give up, and I didn't get it by Monday, and so so I went and I went through a little what do you call it? It's not culture shock, but anyway, I had to get out of that mode. But then 2 weeks later, the answer came to me. And one of the papers was a paper called A Characterization of Parenthesis Languages. It's not a famous paper, but I worked on it very hard, and I thought
Fake languages?
It's parenthesis language. The question is if there's a certain kind of context-free grammar that's called a parenthesis grammar. That means there's a set of delimiters, so that there's a grammar that for every production starts with one of the delimiters and ends with another, and the delimiters are always matched. So that's a parenthesis language, and the question is, if you have another grammar, could you convert it into a parenthesis grammar for the same language? And that was in a time when programming language theory was in the 60s, when that was 1/3 of computer science was studying problems of this kind. And I worked real hard on that, and I failed. But then 2 weeks later, all of a sudden I thought of an idea. So my mind was definitely working on it in the background. And I wrote the paper, and I still think it's a really nice paper, but I've never seen anybody refer to it. And in fact, my book on, I have these books that that's one of the books you don't have. Is called Papers on Computer Languages, and for the last 3 months or so, the book review column in SIGAC News saying, we're looking for somebody to review this book. Nobody wants to take it, and they get a free copy of the book when they review it. But so programming languages, has gone out of fashion. But there were a lot of beautiful problems there, and who knows? Someday it'll come back. But that was one of the papers that when I finished it, I was really happy because the problem had been bugging me for a long time, and I think it's actually a really nice problem.
Wonderful. Legend says, and I'm not sure if it's true or not, but you found the bug in Dick Karp's program for his PhD thesis.
Oh yeah, that was.
So we heard this. Can you tell the story?
Well, you can find it online. I think last year he had his 80th birthday symposium, and I wanted to, Dick had given me a copy of his PhD thesis, 40 years ago, and I filed it away, but never read it. So I figured, okay, I better, if I'm ever going to read it, why not read it before, I'm supposed to give a talk celebrating his 80th birthday, but I knew his thesis was about the traveling sales rep problem, and I was glad when I was reading it to see that here he was a student at Harvard in the 50s, but his thesis was based on machine language code for the UNIVAC-1 computer, and I had also written some programs for the UNIVAC-1 when I was a student, and so the idea was that was one of the practical applications of the traveling salesman problem, because the UNIVAC-1 had a very small memory, and if you wrote a program in a machine language, then if you change the order of the instruction in the program, you could save space, and that was. But you had to have all of the modules of the program in there. So this is a Hamiltonian path with certain cost, of going from one module to another. And so it was a directed traveling salesman problem. And he put that into his thesis, and he illustrated it on a real program for calculating the GCD of integers. And the UNIVAC was a very funny machine when it comes to calculation with integers. It was designed for fractions, not integers. And so he had to go through various strange results. So as I'm looking through his program, I'm having a lot of fun reading Dick Karp writing a program for UNIVAC 1 machine language code. There was no assembler for the machine. There was nothing. It didn't make sense to me, and so I wrote the Mathematica simulation of the program. I didn't have a UNIVAC 1 simulator, and I tried it out on a bunch of numbers, and sure enough, it failed, not getting the right GCD. So that's what I presented to him for his 80th birthday. Okay.
All right, so because it's a von Neumann lecture, let me ask a question about von Neumann. So you are claiming that merge sort was invented by Johnny von Neumann?
No.
Oh.
No. Okay, so I have a paper in another one of those books that you don't have.
You're missing 15 of them.
Yeah, no. It's called Selected Papers on Computer Science, and that's a book that contains the papers that I wrote for a general audience rather than for specialists in computer science. But one of them is called John von Neumann's first computer program, and I had Herman Goldstein showed me the handwritten notes that John made in 1945 when he was trying to figure out how should one specify the machine language for a computer. And they knew how to build computers, but they had no idea what operations code should there be, how many registers should there have, and so he had an idea for a machine that had a lower accumulator, upper accumulator, and then a distributed register that things would go through as they came out of memory and went into the. But he wanted to try it out, and he said, okay, we'll have an add instruction. Let's have instructions for shifting. He worked out certain kind of instructions for branching on conditions. And he wanted to try it out. So the test case for his program was sorting, and the thing that he had to compete with was punch card machines that did sorting, and the punch card machine did merge sorting. IBM had a product. Well, they had card sorters, which was a different thing entirely. It's arithmetic sorting, but they also had a card merging machine, which had two hoppers where you could put decks of cards, and the data on these cards was in order, and then the machine would read the cards, and then it would spew out to on the other side. You'd get one deck that was merged. And so that was a known thing that was IBM manufactured that machine in the 30s. But he said, okay, this is a good test case for a machine language, and so he so he also worked out timing, how long his program was going to take, and he had to figure out how to put things in buffers and move things around. So as he's merging, he has to put partial results in there. So he did actually develop the idea of building up. I mean, IBM machine, you'd have to use it. The operator would have to figure out how to get it going, how to bootstrap it, and getting larger and larger things. So he did add that aspect to the code, but basically he had this program for merging, which he worked out, and then he said, okay, this machine looks like it's going to work. He never published that paper, but when I got a hold of it, I thought, it'd be nice to publish this and show what his code looked like, and I also translate it into a language that's a little easier to understand and explain line by line what he did. So that's my paper on von Neumann.
Any other questions? Well, let's thank Professor Knuth.